couple of minutes brief about Semiconnect before we get started with the webinar. Semiconnect is a freelancing platform which we have started recently, about 2 months back. This is a platform which connects the technical experts to the corporate. So freelancing is very popular in US and Europe. We haven't seen that platform being available for Indian freelancers. So this is an attempt to create a platform where we try to connect individual freelancers who are experts in their domains to the corporates. So feel free to explore more about the Semiconnect platform, and if you have any queries or any information needed, you can always get in touch with us. So as a part of our initiative, because we have expert freelancers available on this platform, we thought of sharing technical expertise with the engineering communities. So we have started this webinar series. This is a second session that we are conducting, and I let Madhu to get started with the session. Thanks, Madhu.
Thank you very much, Sudhir, for that short introduction. Okay, great. So today's topic is going to be on compute express link for heterogeneous computing. So I have around maybe 10-11 slides to talk about and discuss. So what we will do is, instead of taking up the questions in between, we will take up the questions towards the end of the session, where I will ensure that we get around 10-15 minutes just only for discussions, right? So I expect this to go on for about an hour. I'll try to complete within 1 hour. A lot of topics to cover. Let's see how it goes. So straight away, let's jump in. Okay. So we'll start with a bit of a PCIe refresher for some of you who might be new to PCIe. So this is a prerequisite to go further in this session, right? So PCIe is a peripheral component interconnect, which is a off-chip high-speed interconnect for connecting the host processor to peripheral devices. Right? So it's an IO bus. That's how it was developed. It is a packet-based serial protocol device, and if you see, I would like to bring your focus to the figure on the top right. Right, so there are a pair of TX and RX lines shown there, and a pair of TX and RX is called as a lane in PCIe, and multiple lanes are aggregated, and it is called as a link, PCIe link. Right? A PCIe link can be an X1, which means one pair of TX and RX, and it can go all the way up to X32. So that way the bandwidth is scalable. And the bottom left, you see this bar graph that talks about the PCIe speeds, right? So how it has evolved over generations from 2003 till 2019 for Gen 5. So 2.5 gigatransfer per second, it is nothing but the per lane per direction speed. And today we have Gen 5, even though the chips are yet to be out in the market, but the standards are out, and there are already chips that are being made, test chips, etc. And it can reach up to 32 gigatransfers per second. So in terms of gigabytes, you can simply, for example, the Gen 5 speed, you can divide it by 8, and so you will get like 4 gigabytes per second per lane per direction, right? And other important aspect about PCIe is a layered protocol, right? It kind of follows the OSI model, where it has a transaction layer, a data link layer, and a file layer. So the transaction layer is responsible for forming the transaction layer packets. It is also responsible for managing the credits, the quality of service, etc. And below that, there is a data link layer. Data link layer takes care of reliable delivery of data. It takes care of link CRC and things like that. And below that, there is a file layer which has the logical layer as well as the electricals. The electricals comprise of the actual electrical pins and the analog circuitry, and the logical portion takes care of the link training and power management, as well as serial to parallel and parallel to serial conversion and other aspects. So that's in short about the layered protocol. And talking about the PCIe topology, right, you have the PCIe port at the top or at the highest level of hierarchy, which is tightly coupled to the host, and then below that there is a switch, and then you have the endpoints represented as EP here, shown in this diagram. And the switch has one upstream port that connects to the PCIe root complex towards the host, and then various different downstream ports where you could connect the endpoints. And you can also have a topology where there is no switch and you can directly connect the endpoints to the PCIe root complex. That is also shown there. And when a connection is established between an endpoint and a PCIe root port through the switch, it behaves like a point-to-point. It's not a bus wherein like the earlier generation of PCI. So there is no loading of bus or whatsoever happening. It's a point-to-point switch-based protocol, right? And it works on the principle of memory mapped I/O, where the I/O addresses or the device addresses are mapped to the main memory addresses. And other salient feature of PCIe is bus mastering, right? For the endpoint devices, you could have the bus mastering capability, which allows these endpoint devices to carry out the DMA with just some bit of a help from the host system or the root complex. So that's how it works. And there is a split transaction. So that's how PCIe works. For example, PCIe reads are associated with completions that come later point in time, and between the PCIe read request and the completion, there could be other transactions happening on the bus. So that's how the PCIe is architected and constructed. And power management, fine-grained power management is supported, where you could take the link to different low power states, thereby reducing the link power as well as the device power. And quality of service is very important aspect in PCIe, with what is called as virtual channels and traffic classes called TC and VC. You could have very good quality of service. Of course, the credit system and the exchange of credits between the device and the host also allows you to have very good quality of service. So that's PCIe. And moving on, let's spend some time talking about the memory mapped I/O and DMA in the PCIe landscape. So there are various colored dotted lines shown here, right? The one is green. Let's focus on that first. So the green dotted line represents the memory mapped I/O happening from the CPU towards the endpoint, right? So as I told you, memory mapped I/O is nothing but mapping the endpoints, memory and the registers onto the main memory space of the host CPU. Thereby any transactions going towards that address will naturally come towards this endpoint. So the CPU for that uses the load and store operations or memory read and write operations as it would do to the local memory or to its registers. So that's what is an MMIO operation. And then there is a red color dotted line, right? At the bottom you can see. So that's nothing but the peer-to-peer transaction happening between two endpoints without involving the CPU. So that is also possible in PCIe. And then the most important thing is the DMA shown in the yellow dotted line. So DMA engines inside the endpoint allows the endpoint to carry out the bulk transfers between the endpoint and the host memory, right, without involving the CPU. Of course, assisted by the CPU is what this DMA engine works. And to understand how this DMA is configured, at its most simplest level, a DMA could have several start address registers and the DMA size or the transfer size registers and some control registers. right? So these control registers shown in yellow and green, they get mapped as MMIO registers to the CPU address space, and the CPU configures these registers using the MMIO transactions. It is called as base address mapped transactions in the parlance of PCIe. And then once in the control register the go bit is set, the DMA can now independently happen between the memory and the endpoint. So the endpoint now starts, if it is, let's say, the device read, in this case, the endpoint will put a read request to the root port, and as a result, the data will be read by the root port from the memory, and then it will be passed to the endpoint, and the reverse happens in the case of read. So all these things happen without involving the CPU. This also means that these transactions are uncached, right? So they are not cached by the CPU. CPU, as you know, will have its own caches. There is just one CPU shown here, but later on we will also go through a little bit about the caching and coherency aspects. So important point to understand and note here is these transactions happen in bulk, and the control operations are done using the MMIO read and write, whereas the bulk data transfer happens using the DMA. So if you see the time taken to do the control operations versus the DMA operations, so the latency to do the control operations can be hidden behind the DMA operations that happen. So as a result, the issues or the latency seen in programming these control registers is not evident. So it is important to understand that these MMIO reads and writes, they are not very efficient in PCIe because of the several translations involved. So they tend to take more time, and they are very latency sensitive things. So that is something that we have to understand. And PCIe in general is made for this kind of a bulk transfer, where there is a producer that produces the data and somebody consumes the data, like in, let's say, a video transcoding engine or a GPU, where you transfer the bulk of data on which a certain operation has to be performed, and then you set the processing operations, and then once the processing operations complete, the data is again transferred back from the endpoint to the memory. So multiple memory copies also happen, right, between the endpoint and the memory. Now let's focus a little bit on the PCIe Gen5 and the data-centric compute, right? So the CPU, which till some point in time used to be the hero, now has been challenged because of the amount of data that needs to be processed, right? So the compute is becoming heterogeneous. CPU alone cannot do all the compute operations that are demanded by today's applications, right? So you throw in a GPU to do the GPU operations, and then the FPGAs to do certain special functions, and now you also start seeing AI, ML accelerators. Again, they could be a separate FPGA or an ASIC that are being thrown into the compute paradigm, right? So that's what is happening. But on the other side, if you see, the memory is also kind of becoming heterogeneous. So there is a main memory which is based on DRAM, and then there is a NAND storage, and there is storage class memories which behave like memory with persistent capabilities like storage or NAND, and whose cost per bit benefits are also looking much better than say either memory only or the storage alone when viewed in isolation. So, and then there is CSD, what is called as computational storage devices, where computations happen very closer to the memory. So there is a whole lot of new memory devices that are available today, which is making this whole system heterogeneous in terms of both compute as well as memory. So what it means is that in order for us to very efficiently architect and orchestrate this heterogeneous compute and memory, we need a cache coherent bus, right? And this bus also have to be a low latency bus supporting what is called as memory semantics. So because that you have a heterogeneous computing today, so it is very important for all these devices to interact very closely and to share the data in a much more fine-grained fashion, not necessarily at the bulk level, but also at let's say the byte level or a cache line level between, let's say, it's GPU and the FPGA, or between FPGA and the CPU. So memory semantics become very important, and it needs to be these accesses, or these memory accesses need to be cache coherent, because each of these CPU, GPU, FPGA and the accelerators could implement their own caches. They could have their own private memories, and in what is called as disaggregated computing, it is also important to share the available memory within these devices. So in order for us to do all these things, we need a bus, an off-chip interconnect, which is cache coherent, which supports memory semantics, which is low latency and high throughput. So so that's about heterogeneous compute, and let's focus a little bit on PCIe Gen5. Right? So PCIe Gen5, as we saw earlier, it supports up to 35 gigatransports per line, and pretty much the transaction and the link layers of the previous generation of PCIe has been retained with little or no changes, right? And the focus has been only on the file layer optimization. And important feature of PCIe Gen5 is that it supports what is called as alternate protocol, right? So during the link training stage, the device could announce, the PCIe device could announce the capability or the support for an alternate protocol other than say PCIe. So that is an important feature in PCIe Gen5. And so the timelines between, let's say, 2010 and 2017, for about 7 years, PCIe Gen3 was the one which was kind of mainstream, right? It took a lot of time for PCIe Gen4 to arrive, and subsequently between 2017 and 19, very quickly Gen5 arrived. So between this time, I would say between 2015, 16, 17 time frame is when a lot of other protocols like CCIX and Gen Z and OpenCAPI and other things arrived at the scene, right? Because as I told you, the heterogeneous compute was becoming popular, and there was this need to have coherent low latency high throughput bus. So that's where those protocols or those interconnects started coming into play.